Hi, welcome back. In this lecture, I want to go deeper into the variational forms quantum circuit, also called ansatz. I will describe the three more common and most used quantum circuit for variational form. This lecture focuses on the second part or the second stage of quantum neural network. We start first from encoding with our feature map that we described in the second module of this course. We apply then variational form quantum circuit, which is the topic of this particular lecture, and then we apply measurement. The focus of this lecture is on the trainable part of the QNN, the variational circuit or ansatz. So the goal of this lecture is to understand common variational forms, their structure, and how to choose between them. I want to give you a little bit motivation and explain you why the choice of a variational form quantum circuit matters. So the variational forms determine what function and states a QNN can represent. This is also called expressivity. I will say a few more words about expressivity and importance of expressivity, especially during the quantum neural network. They also affect the trainability, so how easy is to train, how easy is to learn, how easy is to go towards a global minimum of the loss function. We will see also some specific topic in this direction about the trainability, so the calculation of gradient, so-called barren plateaus that is related to the difficulty of training, and more in general to the difficulty during the optimization step. A variational form choice also impact the choice of hardware. So if we have a shallow quantum circuit to represent the variational form, this will be easy to run on current quantum computer device. However, if our quantum circuit for the variational form is deep, then it will be much more challenging for us to train it and use quantum circuit. A last point, a variational form choice includes a so-called architecture. So depending on the architecture, we can encode in the structure of this architecture some important concepts like locality, hierarchy, and the problem symmetries. So the variational form, the architecture, also encodes the so-called inductive biases. That is, encoding the structure of the problem into the architecture of the quantum neural network. First, what is the definition of variational form or ansatz? Well, the general definition of variational form is a parameterized quantum circuit, V of theta, with the trainable parameter theta. We apply our quantum state coming from the feature maps. At this point, we have a classical state, feature maps, and we move to a quantum state that is represented by phi of x, and we feed into our variational form that we call the V of theta. So this V of theta is providing another quantum state that we're going to call psi. Then, as last part of our forward pass, we are going to measure this psi of theta. So the variational form and the ansatz is nothing else than this quantum circuit that has trainable, adjustable parameter theta. So theta is a vector which is also corresponding to the weights and the biases of the classical neural network. The very same concepts of variational form or ansatz can be applied to other quantum computing algorithms such as the VQE and other variational quantum algorithms. An important point for us is that designing the architecture of our variational form is analogous to choosing an architecture in classical deep learning. So in classical deep learning, we can choose between MLP, convolutional neural network, transformer. So all these are different architecture for our classical neural network. In quantum neural network, what we do, we choose an architecture which is the variational form quantum circuits, or also called ansatz. Similarly to classical neural network, what we can do is to stack a number of different layers. So as you can see here, we take our phi quantum state coming from the feature maps, and then we have a sequence of different layers. Each layers consists of two main components. The first component is a single layer rotation, also we call it G of R, that takes some parameters, thetas, and a second component, which is the so-called fixed entangling layer. So this is U of ent, right? This is U entanglement. Each layer will consist of two components, one single layer rotation that takes our theta parameters plus an additional circuit whose scope is only to entangle the different qubits. Note also that the second part, the fixed entangling layer, does not contain any parameter. So this is analogous to the classical case where we have repeated weights and activation function blocks in classical neural networks. In this case, we have different layers, layer 1, layer 0, layer 1, layer k to the minus 1, each one consisting of two parts, the single layer rotation with the parameters and the fixed entangling layer that is responsible for entangling different qubits in the quantum circuit. There are three common variational forms, and I'm going to provide you an overview in the next slide. We have the two local, which is an hardware efficient layers with local rotation plus nearest neighbor entangles. We have a three tensor ansatz, which is hierarchical, tree-like connectivity inspired by three tensor networks. And last but not least, we have strongly entangling layers, which provide dense parameterization, so quite a lot of parameters, and the flexible entanglement ranges. Each of these architectures have its own trade-offs in expressivity, depth, and hardware cost. So let's start with the first architecture. The first architecture is the so-called two local ansatz. It resembles the angle encoding feature maps that we saw in the previous module. But instead of encoding the data into the parameters, what we are doing here is to have theta as a trainable angle. So this theta you see here on this diagram of the two local ansatz can be adjusted during the training. This ansatz is QNN with n qubits, and then with the k repetition, which we can think of as layers in a classical neural network. The pattern is the following. We have initial rotation layer, so very similar to the angle feature maps. You see here we have rotation y, which include our tunable parameters. After the per layer rotation, we have a layer that consists of a different control node operation acting on different qubits, and these are our entanglement quantum circuit. So we have for each layer a per layer rotation and an entangled layer. So you see here rotation, then entanglement, rotation, entanglement, and rotation. The algorithm to build two local ansatz is displayed on this slide. The total number of parameters, so the total number of theta that we are going to adjust during the training is n times kappa k plus 1. So the total number of parameters is nothing scaled with linearly with the number of qubits and with the number of repetition. An important part is the difference between this quantum circuit here and the angle feature maps is that this angle here, these times are tunable parameters and are not parameter with which we encoding our input data. When it comes to the entanglement circuit, we have different choices. So here in the previous slide, we have this choice that is a basic linear entanglement. This is nothing else than nearest neighbor C0 pattern. This match 1D nearest neighbor hardware, and the depth grows linear with n. What we can do, we can also have a circular entanglement. So together with our linear entanglement circuit, we have one one additional control node to implement a ring topology by adding one extra long-range entangler. That is this part here. This is our long-range entangler. And then what we can do, we can also implement an all-to-all pattern when it comes to the entanglement. This is called the full entanglement, in which C0 between all pairs of qubits are implemented within a layer. So this is very expressive, so allow us to reach a large number of different quantum states. However, it uses n squared 2 qubit gates, so also implies larger depth and also noise sensitivity. A second ansatz architecture is the so-called tree tensor that we are having here on this diagram. As you can see here, if you look at the diagrams, it looks like a tree. We go from the leaves from this side on the left side to the root. So assuming that we have n number of qubits that can be expressed as 2 to the k, this can be organized in a binary tree of depth k. So the layer 0 is just the application of rotation to all the n qubits. So in this case, we have 8 qubits. To each one, we apply rotation y, taking tunable parameter theta. So the layer 0 apply rotation to all the n qubits, and then C nodes on neighbor pairs. So you see here pairs 1, 2, 3, 4, and so forth and so on. So this is the first layer. The other layers progressively merge pairs into larger blocks via C naught and rotation. So you see now, instead of applying the rotation only, the rotation are applying only to a subset of our quantum circuit. Somehow we are actually merging the contribution of different qubits. So we have these three structures. And the final layers that you see here on the right act on fewer effective degrees of freedom near the root of the tree that is here. This structure provides a natural hierarchical flow of information from the leaves, which take our input into from the quantum state. So here we have a feature maps, is encoding and putting our data in the quantum state. That will be the input of our ansatz. So this structure takes our quantum state as an input and provide here this hierarchical flow information towards the root, which is the output. In this slide, you also have the algorithms that is useful to calculate how many resources we need and how many parameters we're going to have in the tree tensor ansatz. Well, we can have the parameter counts per level follow a geometric series, which has a closed form for the total number of parameters, which is equal to 2 multiplied by n, which is the number of qubits, minus 1. So the number of parameters increase linearly with the number of qubits. As I said, this is a hierarchical structure that funnels information to a small number of qubits at the top. This is very well suited for binary classification, measure a top layer qubit as a decision signal, and also is closely related to tree tensor networks, or TTNs, in tensor network literature. I want to finish up this lecture talking about the third ansatz of variational form quantum circuits, which is called strongly entangling layers. Consider n qubits as an input. In this case, on this diagram, we have 4 qubits and k layers, or repetition. Each layer L applies a 3 rotation that we have here. We apply Rz, Ry, and Rz in series on each of the qubit, as you can see here. After the local rotation, we can apply C naughts according to the chosen entanglement range. The total number of parameters, which are our parameters are theta, is equal to 3 times n per layer multiplied by the number of layers, which is k, for a total numbers of parameter, which is 3 and k. What are the main point of the strongly entangling layers? Well, these are rich single qubit rotation patterns. So we have a series of RZ, RY, and RZ per qubit, which leads to high local flexibility. The entanglement range R of L controls how non-local correlation are introduced in each layer. This is highly expressive ansatz. So we have a lot of degree of freedom because we have several parameters included by this series of RZ, RY, RZ. However, this also means that we have higher cost in terms of more parameters, in terms of deeper circuits. So it's much more complicated than simpler two local forms. So we need to be able to balance between expressivity, that is given by a very large number of parameters, but also consider hardware limits and the risk of over parameterization that put in danger our trainability. I want to finish up this lecture by talking about the concepts of expressibility, which I already used and introduced before. What is expressibility? Well, it is how large and diverse the family of states generated by our variational form quantum circuit acting on the output of the fission map can be as theta varies. If we have high expressibility, the circuit can approximate many different states. So we can express many different states, ideally densely spanning the Hilbert space. However, we have the issue if this expressibility is too high, especially with a deep random circuit, then we have the risk of concentration measure and variant plateaus. It means that the landscape optimization might have a region where our gradient goes to zero is very difficult to explore. So higher expressibility can have a very highly dimensional landscape space, but is very difficult, might be very difficult to explore and to train. On the other part of the spectrum, we have low expressibility, which means only a small restricted subset of state is reachable. If this state expressibility is too low, then we have the risk of underfitting. It means that Q and N cannot represent the target function or state. So what we really want to do is to choose a variational form quantum circuit that is expressive enough for the task. It means that is enough expressed to reach a good number of states that we can use to express our solution, but also is easy to train. So is not too expressive, so the trainability is too difficult. So we want it to be in this area. This is the last slide of this lecture. Talk to you soon.